Hello everyone, welcome to this online course on material science. This is lecture 23 in module 1 on magnetism. If you recall, in the last lecture I have started talking about atomic paramagnetism using quantum mechanical consideration. The atom is a partially filled one, and the electrons in that atom has two different kind of angular momentum. One is the orbital angular momentum, and then the other one is the spin angular momentum, and we want to model the paramagnetic behavior of that atom using this total angular momentum operator, right? And I have shown in the last lecture that the energy of a single electron in that partially filled atom is given by minus the Landé G factor, Bohr magneton, times the magnetic field, and we have the quantum number associated with the ZZ operator, right? Which is the Z component of this total angular momentum. So that's the expression for the energy. So once we have the expression for energy, we usually ask the question is that what is the Boltzmann factor in this problem, right? And the reason we introduce this Boltzmann factor, I have mentioned it before, is that this is the way you introduce the concept of temperature in your system. Actually, what's happening in a paramagnetic model, you are trying to align the magnetic moments of the electron by applying an external magnetic field, right? And let's say the material is paramagnetic, so the moments want to align in the direction of the magnetic field, but the thermal agitation, because the system is a finite temperature, it has this amount of thermal energy which is Kb, right? The Boltzmann constant times the temperature, right? So that's the amount of thermal energy in the system. This thermal energy will try to randomize the alignment of the magnetic moment in the system. That's why we bring this concept of temperature, because in one side the magnetic field is trying to align the moment, and the thermal energy is kind of trying to disrupt the alignment, and it's a kind of competition, and we want to see who wins in the end, right? And the Boltzmann factor is nothing but you have to exponentiate minus the energy divided by the thermal energy, right, which is kBt. And in our problem is nothing but this quantity. So let me put this expression. So for E, we are placing the expression for energy, G mu B, B times mj, and then on the denominator we have kBt, right? And this minus and this minus, they will become a plus. The expression for the Boltzmann factor will be G mu B, B times mj divided, sorry, that should be a plus sign, and kBt, right? And for ease of our writing, we will assume this quantity is some x, right? So this is some x, so that the partition function can be written in terms of exponential of this x times the mg, right? And one thing to note, you remember this quantum number mj, right? This number runs from plus j to minus j in the steps of unity, right? So it starts from minus j, goes all the way up to plus j, so it has twice j plus 1 different values, right? And this is the expression for our Boltzmann factor. And I think I have made a mistake here, and this should be Boltzmann factor, so maybe B dot F. All right, now once we have the Boltzmann factor in our problem, the next thing to ask is that what is the partition function, right? And partition function is a function that is defined as a sum of all the Boltzmann function, right? So if you are not familiar with this function, don't worry, just remember this is denoted by this z, and this is nothing but sum of all these factors, right? And so this is our Boltzmann factors of the system, and we will be summing over all the possible j's, right? Because mj has different values, so we are summing over the mj, summing over the index mj. Now and mj runs from, you remember, minus j to plus j. So that's our partition function, and we need this partition function for calculating different things. But let's try to manipulate this expression a bit to find a more suitable expression. So z is nothing but e to the power x times mj, right? And then we are summing over mj. J runs from minus j to plus j. Now this expression, if you expand, the first term in the sum is nothing but e to the power minus x mj, right? And the second term is e to the power minus x m, sorry, it should be a j, right? Because mj starts from minus j. So let me correct myself. So it should be e to the power x times minus j, and then the second term will be e to the power minus x j minus 1. The third term will be e to the power minus a j minus 2, and this way it will go all the way up to the last term. The sum will be, mj will be j, right? So the last term will be e to the power j times x. So the term before is nothing but e to the power j minus 1 times x, right? That's the expression. And from this expression, I want to take a factor out, which is e to the power minus jx. If you take out this factor, you can see, so you have xj here, you have a minus xj here, you have a minus xj here, and that's why you are left with, so 1 plus e to the power x plus e to the power 2x, right? Because you have 2x here, and you're taking out this jx factor out. In the term just before the last term, you will have e to the power x, and the power is 2 to the power j minus 1, and the last factor will be e to the power x, in the power is twice j, right? That's the kind of series we are looking at. Now we want to convert this series into a geometric series so that we can evaluate the sum, right? And the idea is that we just want to replace some of these indexes, change of variables, nothing else. Let us define that twice j plus 1 is some number m, right? Then what is the value of this twice j? Is m minus 1, right? So this twice j is now m minus 1 in terms of m, right? So now if you are asked to make this variable change in this expression, you will see we have the common term e to the power minus jx, but now in the series we have e to the power x, then e to the power twice x, and then all the way up to e to the power x m minus 1, right? And now you can think that this is a geometric series where the ratio of successive term is e to the power x, right? So that's your ratio. So now you really write this series in like some power k, where k runs from 0 to all the way to m minus 1. So that's a geometric series, and you know the result of the summation, because you remember, right, r to the power m 1 minus r. R is e to the power x, the ratio of the successive terms. So if you just follow this formula here, you will get e to the power minus jx, and then you will have 1 minus e to the power x to the power m, right? And then 1 minus e to the power x. And you know what is the value of m? This is twice j plus 1. So once we perform the summation, now we will get back to our original notation. So now we can replace e to the power x, and then m is nothing but twice j plus 1, 1 minus e to the power x, right? And now multiply back with this factor again. So if you bring back the factor in, you will have minus e to the power gx, and here you will have e to the power j plus 1x, right? And on the denominator you will have e to the power x, 1 minus e to the power x, right? And the trick here is quite common trick once we have a ratio like this, that you bring out some common factors from denominator and the numerator. And the factor we want to bring out, before you want to bring out the factor, let's just change this both this order of these things. So I want to write e to the power j plus 1 first, and then e to the power minus jx, and on the denominator we have e to the power x minus 1, right? So that's our expression. So let's continue. So in this page, our z is nothing but e to the power j plus 1x minus e to the power minus jx, right, from this expression. And then on the denominator we have this, and we want to bring out a factor of e to the power x by 2, right, on the top and on the bottom. So if you do that, you can see the first term becomes e to the power j plus half x, and then e to the power minus j plus half x, right? And in the denominator we have e to the power x by 2, and then e to the power minus x by 2. These two factors get cancelled, and if you remember, this is the difference of two exponents, right? We want to use the formula that e to the power x minus e to the power minus x by 2 is sine hyperbolic x. So this is the relation we want to use for this expression, and then you can see what we have, right? So on the top we have 2 times sine hyperbolic j plus half x, and on the denominator there should be a hyperbolic function. So then on the denominator we have sine hyperbolic x by 2, right, because it's just x by 2. So these two are cancelled, and then the expression for the partition function just becomes sine of hyperbolic j plus half x divided by sine of hyperbolic x by 2. So that's the expression for the partition function in our problem, right? Okay. So once we have the partition function, now we ask the question, how do we find the magnetization, right? And you are applying a magnetic field along z-axis, and you want the moment to align in along the z direction, right? So let's say we are trying to find out the magnetization, and the idea is that there are, let's say, n number of electrons in the atom. So every atom will have some magnetic moment, right? And the moment we want is along z direction, right? So that's the z direction of the magnetic moment operator, right? That's how we define the magnetization of that atom, because every atom along the z-axis has some magnetic moment, which is mu z hat, and that's an operator, and you are just multiplying the number of atoms to get the total magnetization, right? And you remember what is this mu z, right? From our discussion of the previous classes, is that this is nothing but g times the lambda g factor times the Bohr magneton divided by the h bar times the zz, right? The z component of the total angular momentum. And you can see these are just some numbers, and you can bring them out. So we have g mu b times h, and then zz. Now let me tell you something about this expectation value. So if the state is defined, right, we can usually find out this expectation value. And do you remember what's the expectation value of gz? That's just mj times h, right? That's our value. So let's put that expectation value is nothing but mj times the h bar, right? And now the important thing is that in this problem, this expectation is thermal expectation. So you need to consider different Boltzmann weights to find out the expectation value. So although the z operator in the state, so what state we are considering? We are considering the ket mj, right? In this state, this operator has an expectation value mjh. That's fine, but this average can be fluctuate due to thermal fluctuation. That's why we need to take the thermal average of this quantity, right? Because I have told you that although the moments wants to align, but then the thermal fluctuation kind of wants to disrupt this alignment, and that's why we need to perform this thermal average. So that's an average. We have to understand it has two parts. One is the state on which it's operating, but that state can be changed by the thermal fluctuation. That's why we need to perform the thermal average of this quantum number mj. That's the kind of new concept, but don't worry, just I will show you how to perform this expectation value. And this is just a number, you can bring it out, right? And then it get cancelled with this h bar. So we have the expression ng mu b times the thermal expectation value, or thermal average. This is th for thermal, so this is th for thermal. So that's the expression for the magnetization, right? We want to know what is this thermal average, and you kind of know it before, because I have introduced this concept during the discussion of magnetism before. But let me specify this in this context, right? So let's find out what's this quantity really mean. So you remember that the partition function that we define, right, is nothing but we are summing over all the mj state, and the partition function, sorry, the Boltzmann factor is mj times x, right? And we know what is x. X was some factor that we have defined to simplify our calculation, right? And now let us differentiate this partition function, but before that let me mention the value of x that we have considered. This is nothing but g mu b times b kbt, right? So lambda g factor times the Bohr magneton times magnetic field and divided by kbt, that's our x, right? And we want to differentiate this expression, the partition function, with respect to x, right? And you can see the only x is appearing here, so we will have the sum as it is, and we want to differentiate this quantity, right? And then you can see what comes up is the factor mj times mjx, right? And now if you say, okay, what is this quantity? 1 by z dz by dx. So we have this quantity summing over mj e to the power mjx, and what is 1 by z? So here we have a z, and z is nothing but the sum of all the Boltzmann weight, right? So now let me explain what this quantity is. So on the bottom you're summing up all the Boltzmann factors, that's your partition function, but here you are summing up a product, right, where you are forming a product between the quantum number mj times its corresponding Boltzmann weight, and then you sum over, right? So that's how you calculate the average of, and that's how you define the expectation value of mj and the thermal average, right? And which is nothing but 1 by z dz by dx, right? Then we just replace this quantity by 1 by z dz by dx. So our expression for the magnetization becomes g mu b n 1 by z dz by dx, right? Sorry, dz by dx, and that's the expression for the expectation value of thermal average of the quantum number. Now we can write this also in terms of 1 by z dz by db. We are just using some chain rule, and then dv by dx, right? It's the same as dz by dx. You can see the chain rule applied here. Why? Because we know what's this quantity, right? Because x is nothing but g mu b b by kbt. So you know what is dx by db. It's nothing but g mu b kbt, right? So that implies that the dB by dx is nothing but kbt, just flip this, kbt times g mu b. And usually this kbt, or let me define a quantity which is often used in different textbook, the beta, which is inverse of kbt. That's how we define it. So we have a kbt factor on the top, so you can see that this dB by dx is nothing but 1 by beta g mu b. We can place this value of dB by dx in this expression. Let me do that here. So we have m, which is equal to g mu bn, and then we have 1 by z dz by dB, and then dB by dx. For that I am putting this beta g times the mu b, and you can see this g, this gets cancelled, the Bohr magneton vanishes, and sorry, we have the beta here for sure. The g get cancelled, right? So if you just tidy these things up, you will find this 1 by b, which is 1 by beta, which is kbt. So we have kbt, and we have factor of n here. So kbtm, and then this quantity 1 by z dz by dv. So let me write it down in the following page. So our expression for the magnetization is n kbt, and then we have dB by dz. Now our plan now is to model this term, right? How do you find out this factor, which is 1 by z dB by dz? So let me just write this part of the expression. So we have 1 by z, then dB by dz. This is nothing but can be written as the partial of ln z, right? Because you can see from here is that so this is nothing but ln z, then dz by dv, and that's like 1 by z, right? And so this is the chain rule. So instead of this number, you can just write ddb of ln z. So let me now write the term ddb of ln z. This is the quantity, right? The same. That's what can be written in terms of ddb of ln z. So let's try to calculate the value of this quantity. So we know what is the expression for ln z. So let's put the expression for ln, and the z is in terms of this, we have derived it, right? Z plus half x divided by sine hyperbolic x by 2, right? So this is like ln a by b. And ln a by b is nothing but ln a minus b. So we have sine hyperbolic j plus half x, that's ln a, minus ln sine hyperbolic x by 2. So we want to differentiate this term. So what about the first term? So the first term, if you differentiate ln of sine of something, right? So the first is that ln of this one, so this gets 1 inverse, right? So you know the chain rule of the differentiation. So let me apply that chain rule. So we will have the sine hyperbolic j plus half in the bottom from this ln, and then we will differentiate the sine, which is nothing but the cos hyperbolic j plus half, right? That term. And then we want to differentiate, so times, that's x, times the differentiation of this bit, right? Which is j plus half and dx by dv. But we have calculated the value of dx by dv, right? And just a moment ago. So, and that was nothing but the beta, the Bohr magneton, times the lambda g factor, right? And that's the differentiation of the first term. And let me differentiate the second term here. Similarly, we will have sine hyperbolic x by 2. Then on the top, we will have cos hyperbolic x by 2. And then we want to differentiate there will be half, and then dx by dv. And dx by dv is nothing but the beta mu b and g, right? And cos by sine, here we have cos by sine, that's like our cot hyperbolic function, right? You know that expression that cos by sine is nothing but the cot hyperbolic function. So now we need to simplify our expression in such a way that in the end we'll be able to write down the entire expression in much nicer form. So let me clear up this part. So here we have G mu B, stuff like that, right? So maybe let me just check here something. So dx by db is it should be beta G mu B. Sorry. So it should not be 1 by, it should be just beta times like mu bg. So correct yourself. So there was some mistakes here. Now you can write this expression first, that we have this factor, right? Let me write this factor first, G mu b b, right? Then we have this factor j plus half. Let me write it as twice j plus 1 and half here. So don't confuse, that's a beta, not the magnetic field, right? And then we have this cot hyperbolic function where I have twice j plus 1 x by 2, right? From here, twice j plus 1 x by 2. That's the first term, and in the second term we have the same factor. So let me write it here, j mu b beta by 2, right? And then we have the cot function here. Let me write, so the cot hyperbolic x by 2, right? That's what we have so far, and this factor is kind of common, right? Everywhere we have this. And the way we want to bring the half underneath this and half somewhere here to make the expression so G mu B, we have the beta, and we take a factor j common from all these terms, right? So then, and we want to bring the half inside. So now we want to write it as twice j plus 1 and twice j, right? So the factor of j will get cancelled. That's how we want to write. There's a reason why I'm doing this sort of manipulation. You will see soon enough, right? That's the first term. And the second term, we have this part common. We have some 2 here. So 1 by twice j cot hyperbolic x by 2. And if you remember, that's the value of this dB by, or 1 by z dB dz, right? But the magnetization have extra n kBt factor. So once we have this expression, now we can write the expression for magnetization, which is extra n kBt factor times the entire quantity. So we have G mu B, then B, sorry, that's a beta, then G, sorry, the J, and then the function itself. We have twice j plus 1 divided by twice j cot hyperbolic twice j plus 1 x by 2 minus 1 by twice j cot hyperbolic of x by 2. So that's the relation we have. And you can see, what is this beta? Beta is 1 by kBt, and we have kBt here. So that beta and this one get cancelled. So outside we have n, g, mu b and j, right? So let me write m is equal to n mu b g times j. And then we have that function, right? The entire function. twice j plus 1 by twice j cot of twice j plus 1x by 2 minus 1 by twice j cot hyperbolic x by 2. And let us define the saturation magnetization as before. And the saturation magnetization usually is defined by this quantity, right? Let us define that this is our S subscript is for saturation magnetization. This value represents that when all the moments that you apply inside your solid, all the moments of your atom align with the external magnetic field, that's the highest magnetization you can get, and that's your ms defined by this number. And this function is known as the Brillouin function. Let me denote it by B, and you can see we have J here, right? That's a Brillouin function. And sometimes we want to make a change of variable just to make it more convenient. So usually we write is a function of y. And what is y? Y is nothing but xj. So that's a variable transformation. And let's see how can we bring y everywhere in this function, right? So right now you have x here. How do you change x into y? We need extra factor of j. So every time you see x, you put the j and then put some j in the denominator to compensate, right? So the idea is that the function is twice j plus 1, 1 by twice j. We have cot hyperbolic twice j plus 1, right? And outside we have x by 2. In place of x, I will put jx and then add factor j to cancel this, right? That's our y. And on this term we will have 1 by twice j cot hyperbolic. We will put xj here and then the cancelling twice j, right? Xj is y, so you can see now you can write y, you can write y. That's why once you do this variable transformation, this function is known as the Brillouin function as a function of y. And that's why this model is called the Brillouin paramagnetism, right? Because the magnetization follows some function. And if you recall, in the classical treatment of paramagnetism, we also had a function, you remember? And the function was the Langevin function, right? You remember the Langevin. In the next class, I will show you how this quantum mechanical treatment, where the Brillouin function comes up, differs from this classical model, right? For this lecture, I think that's about it, and thanks for listening.